I want to introduce to you the solution of a cubic equation in general. So let's say you have a cubic equation. How do you solve this? Well, this has an interesting history, but I don't want to go through history today. I just want to show you the formula for solving this. If you're given any cubic equation, you can always change this into a form called the depressed cubic. And the depressed cubic is like this. You first divide everything by a. And then you say x is equal to t minus b over 3a. So in other words, you do a change of variables. Saying this is like saying that you have a change of variables t equals to x plus b over 3a, right? You're defining a new variable t, so that you get an equation for t, and if you solve the equation for t, then you can plug that value in to get the value for x. So it's always possible to solve the original equation if all you're doing is just change the variables, okay? All right, so if you plug this in here, you get t minus b over 3a cubed plus b over a t minus b over 3a squared plus c over a t minus b over 3a plus d over a. And I don't want to spend time expanding everything. I just want you to see that if you use the usual formula for expanding a cubic, you end up with the very first term being t cubed, and the next one is, this is a minus, so this is going to be minus 3 times, it will be t squared, but then this will be multiplied, b over 3a. So that these two cancel, and then you will have some other things from this first guy, but then over here you have t squared with b over a, so you get b over a t squared as the next guy, and then plus something. And you can see that these two are going to cancel, and those two places are the only source of a t squared term. So at the end of the day, what happens is that if you simplify this, you're going to get t cubed, and you're not going to get any t squared, but you're going to get p times x, and then q equal to 0, and p and q will be some complicated formula from a and b and c and d. But I mean, you can always do this transformation to come up with this. Alright, so this form is now called the depressed cubic. And if we know how to solve this, then it means we know how to solve this. So we're from now on, we'll only concentrate on solving this one. So let me erase everything. Here's x cubed plus px plus q equals 0. Now let me do something, before we do this one, let's do something even simpler by thinking about the case when p is 0. So how do you solve x cubed plus q equals to 0? How do you solve this? Well, let's think about the simplest case where this q is just -1, right? Because in that case, we know this factorization. So if you were to solve x cubed minus 1 equal to 0, that gives you x minus 1 times x squared plus x plus 1 equals to 0. This tells you that x is 1, and applying the quadratic formula for this part gives you x equals to negative 1 plus minus square root of 1 squared minus 4 times 1 times 1 over 2. Well, 1 squared minus 4 is negative 3. Since you have a negative inside the square root, there's an I. So that's going to give you negative 1 over 2 plus or minus square root of 3I. And yeah, hopefully you've learned the complex plane, because you really need to have seen the complex plane to understand what's going on here. See, the three solutions of x cubed minus 1 equal to 0 are 1, and then if this is the imaginary direction and this is the real direction, then negative 1/2 plus square root of 3 over 2I is like going half, this is negative 1, but here's half step, negative 1/2, half step this way, and then you go up by radical 3 over 2, and you reach this point. Now you can easily check by using Pythagorean theorem that 1/2 squared plus radical 3 over 2 squared gives you 1, so this hypotenuse is 1. And if you've done some trigonometry, you'll notice immediately that this is the triangle that's 30, 60, 90 degrees. So this angle is 60, so that this much is 120 degrees. Okay, so you have this length being 1, this length also being 1, and they have 120 degrees apart. Now, on the complex plane, there's another property of complex numbers of size 1 that if you have two numbers that are on the unit circle so that they're size 1, if you multiply two complex numbers of size 1, what this does is the product becomes the angle, new angle becomes the sum of the two angles. So in other words, multiplying a complex number with certain angle to another complex number acts by rotation. So if I call this as omega, then 1 times omega rotates this 1 by 120 degrees, so you're at omega. But then if you multiply another omega, that gives you another 120 degrees and you're here. And this happens to be the other one. So you can check that if I call the one with the plus as the omega, then if you square that one, you get the one with the minus. So over here, it's at the same exact vertical line. You get omega squared. And then you multiply omega to this again, you come back here, so you see that omega cubed is 1, which is a good thing because omega cubed minus 1 is indeed equal to 0, right? So that's good. And this omega is going to be used for the construction of a general solution. That's why I'm trying to spend some time over here. So you want to know some properties of these omega, this omega. So this is one property. Another one is that omega bar is equal to omega squared. This bar is what's known as the complex conjugate, and complex conjugate means you take the complex, the imaginary part, and you flip it over the real part. So if you take the omega and you flip it over, you get omega conjugate, and that's same as omega squared. Okay, so these are two good properties. Now that we've done the simplest part, let's now try to do some other cases. Well, what if you had something like x cubed minus 8 equal to 0? Well, in that case, of course, you have one solution, which is 2 cubed is 8, 8 minus 8 is 0. So you have one solution as 2, right? Now, if you have just one solution, then you have the other solution as omega times 2 and then omega squared times 2. In other words, if you just find one solution, then you can find the other solutions by just multiplying the omegas if it's in this form, okay? And the reason for that is because you're saying there's one solution there, 2, and omega rotates this 120 degrees to get another solution, and they all have this property that it's 120 degrees rotated in the complex plane, uh, because if you rotate 120 degrees 3 times, you come back to the original. Or maybe a better way to say it is simply if you have x cubed equals to 8, see, if you have 2 cubed equals to 8, then if you have omega times 2 cubed equals to omega cubed 2 cubed, and because we know that omega cubed is 1, this is just 1 times 8, so it's still 8. So we see that if 2 is a solution to this equation, then omega times 2 will again be a solution, right? And then if you have omega squared times 2 cubed, then you get omega 6th power, and of course omega 6th power is omega cubed to the squared, so it's 1 squared times 2 cubed, so it's again 8. So it will turn out that any solution, any cubic equation that looks like this with p equal to 0, you can solve it by first finding one solution, and then you just multiply by omega and then multiply by omega squared. Just to convince you, let me give you a slightly more non-trivial solution, non-trivial equation. Now, in our discussion, we really want the p and q to be real numbers, but let's do something that's not real. So what if I had q as negative I? So for example, what's the solution to x cubed minus I equals to 0? Well, I is here, and you're trying to find something that has, whose cubed is I, so what you can do is you can divide this 90 degrees into 30 degrees, and if you have a rotation by 30 degrees, then 30 degrees, and another 30 degrees gives you I, right? So what you get is this length will be radical 3 over 2, just by using trigonometry. I'm thinking of the hypotenuse as 1. This height will be 1/2. So one solution of this will be radical 3 over 2 plus 1/2 times I. Now, I want you to take some time to actually take a cube of this to verify that the cube of this does give you I. If you already know some complex numbers and complex planes, then what we're doing is kind of trivial, but if you're not used to it, I want you to spend some time to verify that cube of this is indeed I, okay? Now, if I have one solution, what are the other solutions? Well, the other solutions are, from here you go 120 degrees, so there'll be another one at 150 degrees, 120 degrees later it will be 270 degrees, which is here. Yeah, so these will be the solutions, three solutions. Okay, in other words, this is one solution, omega times radical 3 over 2 plus 1/2 I. That's another solution, and then the third solution will be this. See, we are also assuming with the knowledge, we are also assuming the knowledge that any cubic equation will have exactly 3 solutions if you count the multiplicities. That's called the fundamental theorem of algebra. Alright, so that was our quick review of omega. I had to introduce this in order to talk about the general solution. So now, how do we solve this one? Well, so solving this type of equation is called the Cardano's formula. Once again, there's some interesting history behind this, so please read the history for this one. But the Cardano's formula says you start with an assumption that x looks like the following form. It looks like a cube root of some number plus cube root of another number. Okay, so what does that do? Well, if I plug that into here and use this form of the identity, then x cubed will turn out to be the following. It will be cube root of u cubed plus cube root of v cubed plus 3 times cube root of u cube root of v multiplied and cube root of u plus cube root of v added. And then I still have p times x, so I'm going to put p times cube root of u plus cube root of v plus q equals to 0. And then I see that you have cube root of u plus cube root of v appearing here and there. So I'm going to think of these two as like terms, so I'm going to group these and factor this out. Okay. On the other hand, cube is going to cancel the cube root, so I'm just going to get u plus v without anything, so I'm going to group it with this q. Okay. So I have q here grouped with u plus v plus q. And the other guy here is 3 cube root of uv plus p multiplied by cube root of u plus cube root of v. Okay. Now that we have like two unknowns u and v, we have a freedom to let these two u and v to satisfy the following equation. If I choose u and v so that u plus v is equal to q, and 3 times cube root of uv is equal to negative, sorry, this should be negative q and negative p. If u plus v is negative q, then this will be 0. If 3 times cube root of uv is negative p, then this will be 0, so that this equation will be satisfied. Now the question is, can we make that happen? And the answer is yes, because we have two unknowns and two equations. So that means we can find such u and v. And moreover, this is nice because these are what's known as the elementary symmetric polynomials, and there's something called Vieta's formula. Just look it up. If you divide by 3 and take the cube, you get uv equals to negative p cubed over 27. And the way you solve this is by just simply solving for one of them and plugging into the other, right? So just say v is equal to negative q minus u, and then plug that in here, and you get, so these two together, you get u times negative q minus u equals negative p cubed over 27, and then you move this to the other side, so you get 0 equals to u squared plus q times u plus minus p cubed over 27. Now there's still another way, which is to use Vieta's formula to get the same thing. And because the original equation doesn't change when you switch u and v, you're going to find that if I solve this for u instead and plugged it in here, I get an equation for v, and that equation will be exactly the same as this one. So what's happening is that although this is an equation for u, if you found the equation for v, it's the same equation. And because this is a quadratic equation, if you solve using the quadratic equation, then you get two solutions. One of them will be u and the other one will be v. And because in the original form u and v can be switched without changing x, it doesn't matter which one you say is u and which one you say is v. We'll conveniently call the one with the plus as u and the minus as v, okay? So what we're going to do is we're just going to now apply the quadratic formula, which is negative q plus or minus square root of q squared minus 4 times 1 times negative p cubed over 27 over 2. And as I said, both u and v will be these. U will be the plus 1 and then v will be the minus 1, okay? And then if I bring the 2 into the square root, well, first of all, q over 2 is what you get. So you get negative q over 2 plus or minus square root. You're going to get q squared over 4. Minus minus will be positive, and because 2 goes into the square root as 4, 4 and 4 cancels, and you get p cubed over 27, okay? So that's going to be your solution. Now, one thing that we do have to be careful here is that if this is negative, then you get if this is negative, then you get an imaginary number, and therefore when you have to take the cube root, it requires some technical stuff going on here. If this is positive, then you're going to have two real values, and taking the cube root wouldn't be a problem. In fact, if this part is positive, you're going to get that one real solution. Okay. All right. So now what we do after this is see, we use that same idea, but slightly differently. That if this is one solution, the other solutions will be omega cube root of u plus omega squared cube root of v, and then omega squared cube root of u plus omega times cube root of v. Now, why do these satisfy the same equation? Well, if you plug this into here, you'll see that taking cubes, because omega cubed is 1 and omega squared cubed is also 1, what you get will be exactly the same. And over here, because you just have omega in front of here and omega squared here, again, omega times omega squared is going to give you omega cubed, right? So that's going to go away. So at the end of the day, you'll see that having these omega and omega squared into the equation is not going to change any of these things. So that's why both of these are going to satisfy the same equation, and if these are all different, you get 3 solutions that way. Okay. Furthermore, there's a theorem that says if these are real numbers, then if you have a complex number, then the 2 solutions come as a conjugate pair. And that one also makes sense if u and v are reals, because if you take the conjugate, we know that omega conjugate is omega squared conjugate is omega. So these 2 solutions will also be conjugate pairs of each other. Okay, so that's it. That's Cardano's formula. That's how you solve a cubic in general.